So with that, welcome everyone to How to Read and Write Shellcode with our amazing presenter here, Rahil. Do you want to introduce yourself?
All right, hi, I'm Rahil. I've been writing shellcode for like 3 years, I guess. So that's a cool thing about me. So just before we start, I got a couple of things to talk about. So first, it'd be cool if you guys have like some kind of like Linux system open, uh, because I'll have like a little bit of an interactive activity later. And secondly, there will be I will link you that activity so you can download it in the chat right now. It's just a like a binary and the C source code for it. And yeah, so with that, I'll get started. All right. So let's start with shellcode. Before we get started with shellcode, unfortunately, we have to start with assembly. So I'm not sure what you guys' like experience with assembly is. I know that if you have taken what do you call it, CSE 30, you should have like some experience. Oh, you don't have access to it. Hold up. Let me fix that a little bit. Okay. Try again now, it should work. Okay, so this is going to be a bit different than the shell. There is, assembly is when you guys are going to be, yeah, shellcode is different than bash. So I think you guys, if you've taken CSE 30, you probably have a little bit of experience with assembly. I think, I don't know if you've been doing, if it's been ARM for like years now or what, but I know that this year freshmen are doing ARM. Today I'm going to be talking about x86 because that's like what most of my experience is in. It's also what most regular computers. Oh, you still have no access? Oh, new link. There, I'll just paste the link separately. All right, sorry about that. Okay, so yeah, shellcode is going to be basically like assembly that we inject into a program that will get it to do things that it's not supposed to naturally do. Here I'm going to be talking about x86 assembly, which is the most common assembly found in like regular computers like Windows and Linux computers. Yeah, so I'm just going to go over like a few basics of assembly really quickly. So we have the stack, registers, and basic instructions. These are pretty much the three main things that we'll need to know to be able to craft our exploits. So firstly, we have the stack, which is like the basic structure of how programs execute. So when we enter a function, we have a base pointer, which is saved at what we call RBP right here, relative base or R base pointer. The R is just saying the size of the base pointer. So that's where the base pointer is. And then it saves the address of the base pointer, which is right here. And then under that, all the local variables will be like shoved into the bottom. So the stack pointer is going to be at the bottom of the stack, and the base pointer is going to be at the top of the stack, and everything in between that is going to be like local variables. So yeah, right above the base pointer is the return address. And so for buffer overflows, what happens is we basically are writing all the way up the stack, and we overwrite the base pointer and we overwrite the return address, and we change that return address to a different address, and we'll execute some arbitrary code. So That's what the stack is in assembly, just at a very basic level. So this is a 64-bit assembly, by the way. So you'll see that these three things over here are just sitting on the side. RDI, RSI, and RDX. These are what we call registers, which I will talk about more now. Registers are kind of like built-in variables, but they don't exactly act as variables. So each has its own specific functions, and they have like multiple parts. So you see here on this image, it shows EAX, which is like the main first general purpose register, and it's supposed to be a 32-bit register. And you see how it says AX right here. Basically, the first 16 bytes of the EAX register is known as AX. So you can refer to it as AX. And then if you go to the second 16 bits of EAX, you have the bytes AH and AL. And so AH is the top 8 bytes, or 8 bits, sorry, and AL is the bottom 8 bits. So each of them is essentially equivalent to a character. Yeah. So you have EAX, EBX, ECX, EX, ESI, EDI, ESP, and EBP. All of these are your registers. In 64-bit, it just extends it one more length. And so it'll be 64-bit RAX, 32-bit EAX, 16-bit AX, and then 8-bit A higher and A lower, basically. So the second letter is talking about which register it is, the A register, the B register, the C register, the D register. And then the first letter is the size. Are these general assembly registers, or are they unique for 8x86 versus ARM? Yeah, so I think in ARM, right, you don't have ESI and EDI. I think in ARM it's like R1, R2, R3, or something like that, right? You can basically think of EAX as, yeah, it's a bit different with this register. So R1 is essentially equivalent to the RAX register. Yeah, so is basically like R1 is EAX, R2 is EBX. But what ARM does is, because it's a more basic assembly language, it just has like R1 through like 15 or something like that, and it doesn't like differentiate between what registers do. Here, like, there's a couple different like specific things they do. So ESI and EDI don't really work like the other these other four general purpose registers do. ESP, I think SP is also in ARM, and EBP might not be in ARM, but it's like own equivalent. So ESP and EBP, you can't like, they're not the same as the general purpose registers. Like, they have their own specific tasks, and they only do those tasks. But as I'll explain a little bit more, instead of calling functions like we regularly do in like C programs or Java programs, we'll be using system calls, and system calls will instead be using the values in specific registers to execute whatever commands it has to execute. So lastly, we'll go over the basic instructions. Unlike what do you call it? Unlike regular programming languages, you can't just assign like EAX equals 5, right? You have to move data between pointers, right? So you can move EAX comma 5, and what that does is it'll put the value of 5 into EAX. Or instead of that, what you can do is you can use arithmetic operations and bitwise operations to make it 5. So you could say XOR EAX EAX, and when you XOR a register by itself, it just becomes the value 0. And then you could add EAX5, and then that will also be another way that you can add 5 to a register. You can also push and pop things off the stack. So if we go back to the stack, when you push it, it'll go to the top of the stack. And when you pop it, you will pop it onto a register. So if I push like the number 5, it would go to where XX is right here. I push 5, and then I pop it into RDI, and then the value of RDI would be 5. Also, RDI, RSI, and RDX, or ESI, or EDI, ESI, and EDX, they're generally what are going to be our parameters for functions in assembly. Okay, so here's like you can move data. you can do arithmetic operations, you can push and pop off the stack, and you can do bitwise things. So and, XOR, shift left, shift right, etc., etc. And all of these are different like operations you can do. So I'll link you like a little. I'll put this in chat. It's just a quick assembly cheat sheet for you guys to look at when you ever want to make sure on shellcode. So what is shellcode itself? So all shellcode is computer readable assembly code. So it's essentially the same as writing your own assembly code, except for instead of just writing it and executing as a program, you're going to be injecting it into another program in order to finish an exploit. So we're going to be using system calls instead of functions generally. And we're going to be using pure hex values as opcodes and just like inserting it into our programs. There's also this concept called endianness. So in most x86 computers, like the ones that you and I probably use, they'll actually be what we call little endians. So it's the least significant byte first. So I'll explain this a little bit more in this example. But all this example is it's essentially a string, and all it has is a bunch of byte values. So 0x31, 0xC0, 0x50. And when you put it all together and compile it, it actually runs assembly code. And what is this assembly code? Well, here is a little thing. So over here it is, I broke down each of the little snippets of hex bytes into what their associated instructions are. So /x31 /xc0 is just XOR EX EX. /x50 is just push EX. /x68 is push word, and what that does is it'll push 4 bytes basically onto the stack as a word, and then it shows you what those 4 bytes are. It's it's HS//, and the reason it's HS// is because again it's little endian. So if you reverse that, it becomes /sh, and then when you have here is you pushing again /x68, and then this is going to be /bin. Again, it's NID/ because it's supposed to be little endian. Next, so /x89 is going to be our move instruction. So we're moving the stack pointer to EBX. We're pushing EAX again. We're pushing EBX. We're moving ESP into ECX, and then we're moving 0xb into AL, which, if you remember, is the lowest 8 bits of EAX. What that looks like in the end is all this is doing is it's making it so that it's putting the string /bin/sh into EBX. It's putting a pointer to that string in ECX. And then it is moving 0xb into AL, and then it's calling interrupt 0x80. And interrupt is where the syscall actually happens. So at this point, the system will look at the system call table, and it'll go to the value in EAX, which at this point is 0xb, and it'll track what value or what system call is that. In this case, it's the execv system call, which is like essentially like an execute this program. Then it'll go into the EBX and it'll see, oh, we're executing /bin/sh, and that is obviously a file in a Linux computer, and doing that will pop a shell. So the reason it's called shellcode is generally the goal in shellcode is going to be to pop a shell. So let's look into this a little bit more in depth. So we can do this through breaking down a C function. So I will share a new screen. So basically what we have is, I'll link this system call table first. So instruction. Okay, so here we have so here we have a Linux system call table. If we go to the X, so what that exploit was our x86 version. So we can look at the EAX value we were looking at, which was 0xb, which is execv, and all it does is it's looking for the file name, which you put in EBX, and then it's looking for our argv, which is like the arguments you put in, and then environment. So this is going to be an array of environment variables, and this is going to be an array of wow, I'm blanking on the term. Command line arguments, yeah. Command line arguments for whatever program is being run right here. So that's what the system call is itself. But if we look into it, here we are. When we're running, so I just wrote, so I just wrote one malloc command, right? Malloc is like a C function. If you know C, like it just allocates the memory. And so if I call strace, or ltrace, sorry, ltrace on /first, all it does is it calls malloc because that's the library C function that we're running. But if I'm calling strace on /first, it's doing all of this code, and these are all different. So it's calling execv, it's calling brk, which is a different system call, access, openat, fstat, like all these different system calls. And so in order to like do all of this, it would take like hundreds of bytes of shellcode at least. And so that's probably not like what we're trying to do. We're probably not trying to create our own malloc call in shellcode. But what this does show us is that like with enough space and enough shellcode, you can essentially do anything, right? So that's just a really quick example. The source sheet. Now the question is, how do you make shellcode? There's a couple of different ways of doing this. First, you can do write C code, compile it to ASM, and then just extract the shellcode out of it that way. That's one pretty easy way of doing it. But the drawback of this is it won't be using system calls, so that's obnoxious. So you'll have to write the C code with system calls like built in, which again, not the funnest way of doing it. But at the same time, your alternative is assembling ASM. So you'll be using an assembler to write ASM code, and it'll just return out to you the hex bytes that are resultant of that ASM code. So I'll show you guys how to do both of these really quickly. This is just one assembler that I'm linking. Sorry, these are two assemblers that I'm linking. I prefer the second one. Yeah. So I'll link that to you in chat. And then here, let's take a look. So in here, if I want to call execv, I can just call this in shellcode char rb nb environment. All this is doing is calling shellcode, which is just an execv command, right? So simple enough. If I called second, it's just whatever, right? Now, if I break this down in a disassembler, you can see that if all the shellcode is doing is it's calling execv /bin/sh. Now I want to view this in the disassembly. So it's pushing RBP because it's a function, right? All ASM functions start by pushing RBP, moving RBP, RSP, and then subtracting RSP for the amount of space it needs for the environment variable or for the local variables. So because there's two local variables declared, it's 16 bytes or 0x10. And the first one is here, the second one is here, and it will then do all the necessary things that it has to, and it loads into RDI this string /bin/sh, and then it calls execv. Simple as that. That's all the shellcode is doing. This is written on a 64-bit system, not a 32-bit system. So if you go refer to the syscall guide, what it'll show you is instead of loading the /bin/sh string in EBX, you'll actually be loading it into RDI. So that's the one difference. You see 64-bit, all it does, even these are, all these are really doing is initializing null variables to put into the argv and np like variables, slots in the function. So yeah, that's all this is. That's the shellcode, and then if I want to view it in hex, you can see this is push 55, 48, 89, E5 is move RVP, RSP, etc., etc., etc. So you see all these things, and /bin/sh is stored at this string, at this memory location, and that's about it. So that's one way of writing shellcode. Simple enough. Another way is going to be with an online assembler, right? So if I open my online assembler, or even I can just do this here, assemble. Like if I want to push 0, pop it into racks, push 0, and then pop it into RDI, or actually I'll push it into RSI, and I'm going to pop it into RDX. Those are the three argument registers for x86 64-bit, and then I'm going to push /bin/sh. I'll put another like slash in there because it doesn't change anything, and it makes 8 bytes, so it works better. So I'll push that, and then I will move, and then I'll pop it into RDI. Now all I have to do is move RAX, and then the syscall one for execv on 64-bit, which is 0x3b. And then I can just call in 0x80. And this should essentially, yeah. And so this essentially is doing the same exact thing. I just realized I put it in the middle of my shellcode function, which is awkward. But as you can see, I push 0, I pop into racks, I push 0, I pop into RSI, I push 0, I pop into RDX, and then I push this string and I pop it into here. And then because I accidentally assembled it in the middle of my function, it falls through the main, but it's generally not supposed to do that. The next instruction would just be int 0x80. And over here, you can see what all these bytes are. So 6800 is push 0, it's popping into RSI, it's popping in RDX. Each of these have their own single byte instruction code. So yeah, those are the two ways of doing it. Now, like there's a lot of ways to do things in assembly code, just like it is with any programming language, right? You could argue even more ways to do it in assembly, because assembly is like the building block of all programming languages. So, right. So some interesting restrictions that often happen are you'll have ASCII shellcode or no null shellcode, because different functions in C will actually stop reading strings after null bytes. And also, oftentimes if you have to inject shellcode, it'll be into like a text box, for example. And if you are inputting something to a text box, and you can't really put like an ASCII code 0x like, or you can't put like an ASCII code 0x like 95 because that's not an ASCII character, right? It would just like not eat your input. So ASCII shellcode and no null shellcode are two interesting examples. And ASCII shellcode actually has like a lot of instructions that are usable. For example, like all the XOR instructions are usable. Push, pop are both usually accessible. Stuff like that, right? So that's one interesting restriction that can, or those are two different interesting restrictions that can happen. But for now, we'll do the activity now. So if you download the files earlier, I will share it and like talk over it a little bit just for a second. Um, okay. So this is the C code for what the triad activity is. Oops. So all it does is it gives you a buffer of 50 bytes, and in those 50 bytes, you have to write your own shellcode to pop a shell. So you can do this using the execv/bin/sh, but there's a couple of restrictions I put on this. So it takes in exactly 50 bytes, and then it loops through these 50 bytes and it looks if you have a 49, a 50, a 51, 52, or 53 in your shellcode, which are all the ASCII characters that do XORs. So no XORs are allowed. And then also, um, you are not allowed to have two null bytes side by side with each other. Okay, so those are the two restrictions I put. There's a bunch of different assembly instructions you can use to do this, and essentially the goal is you're going to be so essentially you're going to be opening your syscall table. You're going to be looking at your execv, and you have to find a way of fitting in the /bin/sh file name and zeroing out both the uh, RSI and RDX registers and setting the RAX register to 0x3b. So that's your goal with these restrictions. Yeah, so good luck. If you have any questions, just type them in chat and I'll just answer them as we go. And at the end, I'll show you what my solution was. I'll give you like 10 minutes to do this. If you needed to do something like, in this case, we have to fill the entire buffer, because if we don't fill the entire buffer, like to up to 50 characters, what C does is it will automatically fill the rest of it with null bytes, which will make it fail the last track. So if you don't want the code to do anything, but you still want it to pass something like this, what you could do is you could have leading or trailing, what they're called is no-op operations. So NOP in assembly, which is just the 0x90 character. All they do is like literally nothing. They just are used to pad space. So that's one cool thing. And I think like my solution was like 30 some bytes. So because of that, I had to fill in like 15 bytes of what are they called? Yeah, no ops. And it's called a no ops sled when you have like a chain of them. Good amount of time. Did anyone actually manage to like write shellcode that satisfies all those conditions? It's like a thumbs up or something weird too. No? Okay. I'll just really quickly go over my solution, and then we'll keep going with this. So the way I solved this was I thought of first, the most important issue is how do I make sure that the RAX register is empty, and then I can put in the correct value into it without it having something like some other random characters or like random bits ticked on the upper bytes, right? Because at this point, the only things we can do are like byte-wise operations with null, otherwise it won't pass the check. So in the end, we're gonna have my solution pulled up right here. So what I decided to do was I just pushed pushed the null byte onto the stack twice. I popped it into RDX or RSI in the beginning, and then that was only one single null byte at a time. So because of that, then I could move the string /bin/sh into RBX, push RBX, which will then push that value onto the stack. You can technically push this value onto the stack as well, but I think it takes more bytes technically if I did that. So then I push RSP, I popped the /bin/sh string into RDI, and now my RDI string is /bin/sh. My RSI and my RDX are both null, and I moved 0x3b into my racks, and because I pushed racks in the beginning, it was empty. So yeah, so this will make all my registers work, and then I use a syscall. Now, another important thing is how you actually use this in an exploit. So depending on how much experience you have with binary exploitation, there is this cool library in Python called Pwn. So in the Pwn library, what you can do is you can first create a process using this process, the process command. So you have to import Pwn, and you can install it through, I think you can install it through pip. It works through Python 2 or Python 3 if you're, depending on whatever you like. So you can run programs with the process, which is native to Pwn. Then you can also use GDB to attach it to processes. So this is what I use for debugging to look at my shellcode. So I can do gdb.attach, and it'll attach to this process. And I can also set a script to run as it attaches. So as soon as it attaches, it will break at this address in the function or in the program, which was in the middle of the main function. So right before it actually did any of the checks. So I could just make sure it went through all the checks properly. And if it was failing one of the checks, I could see which check it was failing. So GDB is a really cool tool that you can actually use with this. And then also all you can do with it after that, you can still send and receive bytes. And then they have this cool feature called interactive. And so if you're popping a shell, you'll need to interact with the process at the end of the execution of it. And so interactive, all it does is it'll receive all the bytes, it'll push it, it'll flush the buffer, and then it will essentially give you standard access to the program. So if I run my program, oops, oh, does is it gets that, I can continue, and it'll break right before execution actually. And I can step through if I want to. And now you can see my shellcode in GDB. So it pushes racks, pushes those, pops those values into it. You can see my racks is 0, RSI is 0, and RDX is 0. My RBX has /bin/sh. And then pop it into RDI. So now right here, my RDI now has the a pointer to the string /bin/sh, which is necessary. And now with all of my registers, and I can just call syscall, and boom, I have executing a new program /bin/dash, and now I can close this and I have a shell, right? So that's cool. This is really cool because a lot of times you'll have to interact with the program. So if the program will only allow me to do something after I give it a certain after it receives a certain input. So if I had a bunch of different prompts where I had to select the right option in order to get to this prompt where I can insert the shellcode, I can use receive until, which will receive until a specific string, and I can use that to tell like where I am in the program execution. So for developing your exploits with shellcode, Pwn tools, the Pwn library in Python, Pwn tools, is really useful for just doing stuff like that. So moving on from there, uh, the reason shellcoding isn't just an exploit by itself, the reason why it generally has to be chained together as like the end of like a complex exploit is because unfortunately there is the nxbit or the WXOR bit. So in Linux, the way memory works is it's allocated in pages, and in each page of memory, you can a bit can be set so that it's either writable or executable, which is the NX bit. So the NX bit makes it so that our memory is not executable. So if I just type in shellcode like that, I can't just run it. So that's kind of an issue for what we're doing. The NX bit kind of destroys shellcode at its most basic, but there's a little bit there's more complex exploits that can be had through shellcode. Again, shellcode isn't just used for making shells. You could do privilege escalation vulnerabilities, like using SUID binaries with shellcode. That's another common usage of it on Linux. I think those are like the two most important uses of it on Linux. But on Windows, the NX bit, which on Windows is called the WXOR bit, is a part of this thing called data execution prevention, which can be turned on and off. And in Windows, these exploits, there are some exploits that are often commonly used, where they'll use a different, more complex exploit that has less limited capabilities called a ROP chain, and they'll build a full ROP chain to turn off this execution prevention, which essentially unticks the WXOR bit, and with that they can execute shellcode on Windows systems. So shellcode isn't dead, but there's a lot of different ways that you need to. There's a lot of complex other steps you need in order to actually bypass all of the protections on shellcode. So shellcode is often like the least complex part of a long exploit, but it's still a necessary part to understand because without being able to write shellcode, you can't do any of this. There's a lot of different other reasons that you need to learn how to write shellcode because there's a library in C called seccomp, which will restrict a lot of instructions from actually being called in Linux, and I'm not sure how it works in Windows, but I know in Linux there's a library called seccomp, which will stop a lot of library calls or system calls from being executed. And so knowing different system calls in order to execute the same functions is really important. So yeah, there's that. There's a couple more resources I wanted to add here. To learn a little bit more about shellcode, I left all these links, which I will drop in the chat really quickly. There's also two websites that have a lot of pre-written shellcode, which I will also show you right now. So Shellstorm, does it show the tab? Does it change the tab properly? I'm not sure. When I do that. So Shellstorm, what it has is all these different kinds of shellcode for different architectures and for different things. So you can change your user ID. You can call break chroot. You can port bind. You can pop a shell. all in different kinds of architectures. There's BSD, Cisco, there's ARM, so these are a bunch of different ARM ones. They're also different sizes, 34 bytes, 79 bytes, etc., etc. Strong ARM, MIPS, like x86 64-bit, x86 32-bit, which, yeah, x86 32-bit, all these different kinds of shellcodes that do different kinds of things. And there's different encodings on all these shellcodes and stuff like that, which can change the sizes of them. And it's all just different ways of doing the same kind of thing. So that's what Shellstorm does. There's also, this is just another PowerPoint on a bunch of different ideas about shellcode and how to use it, and how to exploit, to write exploits with it. And then lastly, I have this one I found. It's called Ring Zero CTF, and they actually have like 7 shellcoding challenges, all with different levels of difficulty, with different kinds of things that you can do with it. And so I think these are just really cool things if you're interested in practicing. They're just good stuff. If you are familiar with Pico CTF, generally they'll have 1 or 2 challenges a year that have to do with shellcoding, and they'll also have a couple of challenges that deal with reverse engineering assembly code, and that also really helps with learning how to write shellcode, because reading shellcode and writing shellcode are both pretty similar tasks that are pretty interwoven. Actually, I can show one more thing, which is reading shellcode. Like personally, so one program that I use to do a lot of reading of shellcode is Binary Ninja. You can just basically open any of these binary files. So right here, I open this, I go to my main function, and it shows you in different, like, varying kinds. So there's a high-level language and disassembly, and the disassembly is essentially our shellcode. So this is all the assembly code that's being used, and I think that's a fascinating way of learning. Another thing is, if you're like GDB, if you're familiar with GDB, GDB without debugging symbols also gives you raw assembly, and so that's another way you can learn assembly stuff. Yeah, cool. So do you guys have any questions before? That's pretty much the entire talk. If you have any questions, I can answer. If you have any questions about like what you can use shellcode for, about like exploits that use shellcode, or like practical usage, or like practice with like CTFs or something like that, I can answer any of those. What was the checking code? I think it was, if you just scroll all the way up in the chat. These platforms. Oh no, it's still totally applicable for like Windows. That's the cool thing about Shellstorm here, which I will show you. So because both Linux and Windows, like most Windows and Linux computers, still both run on x86. Both of these exploits are still like usable for either. So instead of calling execv/bin/sh, you'd be calling execv c:/Windows/system/system32 or something. So yeah. It's pretty. You can even actually call shellcode on like mobile phones or like routers and stuff like that. Another thing that's cool is because a lot of IoT devices and stuff will have less protections than like normal like computers and phones would have. So a lot of IoT devices would have less protections against shellcode. And if you can find a way to inject it, it'll probably run better. Like there'll probably be less protections like NX or WX or X on like IoT devices, like an IoT fridge. Yeah, it's like it's a matter of ARM versus x86 versus like MIPS. You can do it with everything. It just depends on like your practice with it and stuff like that. If you know ARM better, then you could also write shellcode in ARM. I think generally, from my experience, ARM shellcode actually for calling /bin/sh is, I think the shortest way of doing it is actually longer than with x86 because I'm not sure why, but because some of the instructions just require like longer opcodes. Anything else?
Okay, so with that, I guess we're done then, right?
Yeah, I ran a little bit quick.
All right, thank you, Rahil, for the awesome shellcode workshop. I don't know, do you have any last minute remarks?
No, thank you for having me.
All right, well, thanks for showing up, everybody. We'll go ahead and we'll end the workshop here then. Bye, everybody.